Hello students, I hope you're well. I got a request to do a video including a couple examples of derivatives that involve more than one rule at the same time. So I found a couple examples that are a little bit complicated to hopefully give you a little bit of practice and review a few things that you may have forgotten over the break. The first problem says I should take the derivative d dx of e to the 2x times 5x cubed minus 12 over x to the 4 plus 6 all raised to the 10th. This looks really nasty. There's a lot going on. You definitely have some inside functions and outside functions, right? I mean, we have all of this stuff where we expect the x to be in the polynomial expression x to the 10, so there's going to be a chain rule. We have the 2x in place of where the x is supposed to be in the exponential function, so we have another chain rule there. And we also have a product. But which things do we do first? The way I think about it is I try to work from the most zoomed out perspective to the more zoomed in perspective. So if I really stand back from the problem, it looks really like I've got this stuff times all of this stuff, right? So I can write this whole big thing as a product. So the first thing I'm going to do when I take the derivative of this expression is do the product rule. Before I do any of that, I'm just going to write down the problem because I want to keep my work really organized. So I'm going to do the derivative of e to the 2x times 5x cubed minus, and instead of writing 12 divided by x to the 4, I don't want to do the quotient rule when I take the derivative of this part later on. So I'm going to write this as 12x to the negative 4 using my negative exponents because I know the power rule works for negative exponents. So I included that little bit in there just as a reminder that you shouldn't always use the quotient rule if you don't really have a quotient of two interesting things. Here I just have a constant over something, so I should treat it as just the x raised to the negative exponent 4. Okay, plus 6 all raised to the 10, so that's what I'm taking the derivative of. And the product rule says take the derivative of the first times the second left alone, and then switch the order, so take the derivative of the second times the first left alone. So I'm going to write down that I'm going to do that without actually doing that, because that way I'll set myself up for the right steps, and I'm not going to get confused by trying to do more than one thing at once. So I'll take the derivative of the first times the second left alone, 5x cubed minus 12x to the negative 4 plus 6 all raised to the 10. Plus, I'm going to do the derivative of the second, 5x cubed minus 12x to the negative 4 plus 6 all raised to 10. And then I'm going to multiply all that by the first just left alone. Notice again, I'm just saying this for emphasis, but I didn't actually take any derivatives here. I just wrote that I was going to take derivatives, and I'm working my way from the biggest zoomed out perspective towards the inner nitty-gritty details of the expression. All right, what's the derivative of e to the 2x? Well, I do know that the derivative of e to the x is just e to the x, right? And this is sort of like e to the x. I could pretend like it's e to the x if I cover up the 2x that's in place of where the x is. If I had the derivative of e to the laser pointer, the derivative would be just e to the laser pointer. So that's what I'm going to write down. But because what I covered up with the laser pointer wasn't just x, I have to multiply by the derivative of what I covered up. All right, so just to go over that one more time, we have the derivative of e to the blah is e to the blah. But the blah was not just x, so I have to multiply by the derivative of the blah. Okay, and then I'm just going to leave this whole thing here, 5x cubed minus 12x to the negative 4 plus 6, all raised to 10. And over on this other side, on the right, now I have the derivative of this stuff. Hey, this is also a chain rule situation. I have all of this in place of where the x is supposed to be in x to the 10. So the derivative of laser pointer line to the 10 is 10 times laser pointer line raised to the 9, right? So that's what I'm going to do. 5x cubed minus 12x to the negative 4 plus 6 all raised to the 9. And then what I covered up with the laser pointer wasn't just x, so I'm going to multiply by the derivative of the inside, 5x cubed minus 12x to the negative 4 plus 6. And then I've still got my e to the 2x hanging out here. Just like in the last step, I didn't do all of the things at once. I just wrote down what I was going to do. All right, in the last step now, I just have the derivative of some polynomial-like things here. We've got e to the 2x times the derivative of 2x is just 2. We still have this expression here, 5x cubed minus 12x to the negative 4 plus 6 all raised to the 10 plus. Then on the second half here, we have 10 times the inside stuff to the 9. All right, now what's the derivative of all this? Well, you can just use the power rule on all of it, even the one with the negative exponent, because we showed that the power rule works when you have a constant times x to the negative exponent. So here we go. The derivative of 5x cubed is 15x squared. And the derivative of negative 12x to the negative 4 is going to be, well, we bring down the negative 4 and multiply it by the negative 12. So what is 4 times 12? Well, that's 40 plus 8, so that's 48. And it's going to be positive because the two negatives cancel out. Times x to the negative 4 minus 1 is negative 5. So, and then the derivative of 6 is a constant, so the derivative of 6 is 0. And then we have multiplied by e to the 2x over here. So now we're pretty much done. And you know, we could certainly factor some stuff out. Like we could factor out this common e to the 2x here, and we could factor out 9 of these things. I guess I'll do that just because we can, and it'll give us some practice factoring. And then I can factor a 2 out of here and a 2 out of here. So let's see what we get here. So I'm going to factor out, first I'll factor the 2, then I'll factor the e to the 2x, and then I'll factor 5x cubed minus 12x to the negative 4 plus 6 all to the 9. And let's see here. In the first term, what do we have left over? Well, the only thing we have left over is 5x cubed minus 12x to the negative 4 plus 6, because we took out, 9 of these, and we took out the 2, and we took out the e to the 2x. All right, what's left over in the other one? Well, we took out 2 from the 10, so there's 5 left. We took out all of these, so that would be times 1, or we don't need to worry about that because we're multiplying by 1. So then we have this term, and then we factored the e to the 2x out already. So the only thing we need to multiply here is times 15x squared plus 48x to the negative 5. And the zeros doesn't need to go there because it's just 0. All right, so here we go. We got this, and I don't know. I guess I'm in the habit of simplifying, so I'll just write one more step. 2e to the 2x times 5x cubed minus 12x to the negative 4 plus 6 all raised to the 9 times. All right, well, if I put them in descending order here, the highest one is 5x cubed. Cubed is the highest. And then I've got an x squared term. It'll be 5 times 15x squared. So that would be, what? 50 plus 25 is 75. X squared. Okay. So that takes care of the cubed and the squared stuff. And then I'm going to put maybe the 6 next, because that's the x to the 0 power term. Then I have the negative 4 and the negative 5 stuff to go. So negative 5 is more negative, so I'll leave that to the end. So I'll just write negative 12x to the negative 4 plus, and okay, now I got to do 5 times 48 times x to the negative 5, and 5 times 40 is 200. 5 times 8 is 40, so that's 240. X to the minus 5. And you could certainly write x to the minus 4 as 1 over x to the 4, and x to the minus 5 is 1 over x to the 5, but I'm just going to leave it like that. So hopefully you enjoyed that one. All right, here's problem number 2. So this one says find the derivative of y equals the quantity tangent of 3x all over x all raised to the 7. So this one has got a lot of stuff going on too. I would say if I squint at it and look really far back, at the outset it looks like the blah raised to a 7. So this is really a chain rule situation. So let me write the derivative of y. We could call it dy dx, or we could call it y prime. I'll just call it y prime for now. And that's going to be the derivative of all this stuff Tangent of 3x all over x 7. All right. So now that I've written down what I'm going to take the derivative of, now I'm going to do it. And as we talked about before, this looks like a chain rule because I have a blah raised to the 7. So here we go. We've got 7 times the blah to the 6, because if it were x to the 7th, the derivative would be 7x to the 6th. Okay, but what I covered up in the middle, tangent of 3x over x, wasn't just x. So I've got to multiply, because of the chain rule, by the derivative of that inner function. Okay, let me just go over that one more time. I have the box raised to the 7. The derivative of box raised to the 7 is 7 times box to the 6. But when I uncover the box, this stuff wasn't just x, so I have to multiply by the derivative of that. And again, like I did at the beginning of the first problem, I wrote down what I was going to do, and I didn't actually take the derivative of that inside function yet, because that'll mess me up because it's too many things at once. Okay, so here we go. Now notice, this inside function, tangent of 3x all over x, is a quotient. So we could do the quotient rule when we're taking the derivative. But if you didn't want to do the quotient rule because maybe you wanted a change of scenery, you don't like the quotient rule, maybe you want to do the product rule instead, you could write this as tangent of 3x times x to the negative 1. And if you did that, then you could just do the product rule instead of the quotient rule when you're taking the derivative of that inside part. But because we didn't do the quotient rule yet, I'm going to use the quotient rule. But just keep that in mind. There's not just one set way to do all these problems. You have some freedom of choice. Math doesn't always just have a right answer. There's some multiple different approaches that you can take, which is pretty cool. All right, so here we go. The quotient rule says low d high minus high d low all over the square of what's below. I'm going to do low d high minus high d low all over the square of what's below. Okay, and again, I just wrote down what I was going to do. I didn't actually do all those derivatives because I don't want to get myself confused. Lo and behold, this first part is another chain rule situation because you got 3x where the x was supposed to be in the tangent function. All right, so here we go. The derivative of tangent of blah is secant squared of the blah. But the blah wasn't just x, so I have to multiply by the derivative of the blah. So that's what I'm going to do. Subtract tangent of 3x. Okay, and then the derivative of x is just 1. All over x squared. All right, my final step here, I've got 7 times tangent of 3x all over x raised to the 6th times x secant squared of 3x. The derivative of 3x by the power rule is 3. 3x, y equals 3x is a line with slope 3. You can think about it that way. The derivative is slope. Okay, and then I have minus tangent of 3x. And I have everything divided by x squared. I don't know if there's much way to simplify this, so I'm just going to leave it as is. You can't cancel the x here and the x here. Why not? Because there's no x in this term over here. So don't do that. In order to cancel things, you have to factor them out of the whole top and whole bottom. Okay, so here were 2 examples of problems involving multiple rules at once, and hopefully you enjoyed it. Let me know if you got any questions. Of course, you can send me an email. See you later.